Okay, so first things here, we've got, let's see, smaller. Okay, so first thing, notice we have intercepts. Obviously, that numerator is 0 when x equals 0. However, you might want to also notice that this numerator has a common factor with the denominator. So it agrees with this function, except that, of course, x is not equal to 2. Okay, that means there's a hole there. That's what that tells us, hole at x equals 2, because the division by 0 divided out. So we have intercept x equals 0 only. Second, we have a domain x not equal to plus or minus 2. Okay, there's a hole at 2, so let's investigate what's happening with that domain. Or 3. Well, first of all, vertical asymptote at x equals negative 2. You can see that here. And there's a hole at 2, and its value will be this. The limit as x approaches 2 for this expression, which is actually 4 over 4, which is a 1. So it was a removable discontinuity. Okay, hole 2, 1. There's a hole right there. Okay, now 4. Let's look at extrema. Extrema. Okay, find a derivative f prime. We're working with this guy here. 2x times the denominator minus the denominator's derivative, which is a 1, times the numerator all over denominator squared, which is 2x squared plus 4x minus x squared, or x plus 2 squared, and that's going to give us x squared plus 4x over x plus 2 squared. Okay, when you set that to 0, you notice the numerator, so it'll be x times x plus 4. So we'll have x equals 0, and we'll have x equals negative 4. These are critical. Okay. X equals negative 2 is not critical, because we already saw that was a vertical asymptote. So, but we will keep it in mind if we should. Let's use our first derivative test for that. Let's set it up. And we've got a couple points here. We've got a negative 4 and we got a 0. So we're going to have to test around it. Let's try a negative 5. And we have to watch out for that vertical asymptote at negative 2. In fact, I'm going to put that in here just to be aware of and watch out for. Okay, don't want to pick that. I want to pick around it. So I'm going to pick another number in here, like negative 3, and then I'll do a negative 1 and then a 1. So a lot of stuff going on here. F prime here is 0, and the other one was 0. It's 0 here. And here it's at negative 2, undefined. Okay, so we're going to fill in the blanks in here. I use a different color for this. Oh, that's kind of thick. Okay, so let's go ahead and check our derivatives then. F prime of negative 5. And we'll work with this one here. You'll see a 25 minus 20. Denominator is positive, so don't even worry about that. That's positive. So we've got plus going in here, plus, plus, plus. Let's try that negative 3 now. f prime negative 3. Be a 9 minus 12. Numerator, that's negative. So it's negative in here. Okay, now let's try the negative 1. That'll be 1 minus 4. That's also negative. Let's try the 1. That's 1 plus 4. That'd be positive. So what this tells us, the chart tells us, is that the function to the left of the negative 4 is coming up, and it smooths out at 0 slope, and it's coming down to the right. Now, it's heading to its asymptote, so it's negative. And so you can kind of imagine an asymptote in here. And then it's negative on the other side, so it means it's coming down from that asymptote. And it comes down, it levels off to 0 slope here, 0, and then back up. So we can see pretty much what the graph's doing. Here you have your relative max, and here you have your relative min. So next, only thing left to do here is let's look at finally those coordinates. So 5. Let's look at the coordinates now. So we have f of negative 4. That was, go back to your original function, and which we're actually using this one here. Okay, so a negative 4 would make it 16 over negative 2, which is a negative 8. Okay, f of our other critical number, 0. Well, we already calculated that one. That was a 0. Okay. So let's see if we can put all this together then on a graph. We'll do a graph down here. Okay, so you got an asymptote at negative 2. Okay, and you have at negative 4 a relative maximum. Okay, that's what we saw. Yes, okay, relative maximum. So we know at least in this neighborhood here, it's coming like this, and it's going to head down to that asymptote. Okay, to the right, we stay. Okay, to the right, you have, there's a 0 right here, and it's also the minimum. So it's coming in, whoops, coming in like that. And at x equals 2, so it was a 1, there's a hole. It's coming through like that. It's rounded, coming out of there like that. And then heads up, basically like that. I mean, there's nothing else it can do. So once we come in like this, and the only other thing is, okay, this must come down like this and head out to infinity. I want to show you something else here that we haven't talked about yet. And this is a good place to introduce it. We have what's known as this function. Go back to the original function, which really is this one here. After we cancel that hole out of there, reduce that hole. If we do a division, what we can see as x goes to infinity, this does not have a horizontal asymptote, okay, because the numerator has a higher degree. So what you do in this special case is that, and you can do this for lots of graphs, but we're only going to do it when if the degree in the numerator is 1 higher. So we have a rational function. The degree in the numerator is exactly 1 higher and denominator. We have what's called slant asymptote. Okay, let's talk about that slant asymptote again here. We are at, okay, so here's how you find it. You've got your x squared over x plus 2. And what we're going to do is a long division. We're going to take this, divide it. So we'll have an x up here, x squared plus 2x. And then we'll have a minus 2 here. So our expression, our function, really looks like this in another form. Now notice it, what happens as x goes to infinity? If x goes to infinity, this term heads off to 0. And this doesn't head to 0, but you could say the function behaves like this line x minus 2 way out there. So what we do is we say that is the slant asymptote. Y equals x minus 2 is what we call slant asymptote. So if you were just to lightly draw in an asymptote running this way, that's the line x equals 2, or sorry, x minus 2. And then you would have a better idea of what this, this curve did over here when it came through. It's coming through and coming down like that, heading out that way. So that's a little bit more accurate picture of how that curve behaves there. And likewise up here in this region, it doesn't head up just sort of like up that way. A little bit better description would be that the graph heads out this way, out towards that line. So I would remove this part here. Whoops, and let me fix that. And just have it come in like that. So it heads out towards that line. So this is a little bit more accuracy when we take into account the so-called slant asymptote. And it occurs only if the degree in the numerator is exactly 1 higher than the degree in the denominator. So here we have all the attributes and characteristics of this graph. We've got the relative minimum, relative maximum over here. Notice how counterintuitive that is. This is relative maximum, but it's a lower point than this one. It almost seems like a contradiction in terms. A relative maximum, which is lower than a relative minimum. But the key is that it's relative to this region of the graph. It is a maximum. Likewise over here, relative to this region of the graph, it's a minimum. And of course, there's our hole. Okay,